What we'd like to talk about in this video is the magnetic force law. So just like the electric field had a force law, well, there's a force law for magnetism as well. The electric force law was this one. It says, rather simply that if you have a charge, Q, in an electric field, then the force on the charge is just going to be Q times E. Just multiply the field times the charge. That will give you the force. So a positive charge in an electric field is going to move, in this case here, to the right. So positive charges, as we saw, always follow E. And of course negative charges, because the Q will be negative here, sort of go opposite to E. They sort of go the other way. So if we put a proton in a field pointing to the right, the proton will start moving to the right. If we put an electron in a field to the right, the electron will start moving to the left. So that was the electric force law. Pretty simple, very nice, blah, blah, blah. But now what we're doing is the magnetic force law, and it is an entirely different animal altogether. So what we'll do first of all, we'll say, okay, it has to do with a charged particle, and it also has to do with a magnetic field. Let's write the law up first, and we'll sort of diagnose it a bit more. It looks like this. It's QV cross B. All right. So it has that cross product in it here. It relies on two vectors in the cross product, and you can catch another video that describes the cross product, how to figure some things out with it, and you can go with it. So unlike the electric law, well, first of all, let's say like the electric law, the force here does depend on Q. So the object in the magnetic field has to be charged, and of course there has to be a field present. Okay? That's probably pretty clear. Looks a lot like the electric force law, which was Q times E. There has to be a charge and there has to be a field. Here there has to be a charge and there has to be a field too. The big difference between them is that in the magnetic case, there has to be a speed. In other words, a charge has to be moving also, or there'll be no force on it. So yes, it's true. If I draw a magnetic field line, a bunch of magnetic field lines like this, something like this, and I place a proton right in that magnetic field line, but I don't give it any speed. I give it V is equal to 0. Proton's not going to move anywhere. Or if I put an electron in here and don't give it any speed, it's not going to move anywhere. Again, you can contrast that with the simpler electric law, F is equal to QE. You can contrast it with that, which doesn't matter if the particle's moving or not, this force will be imparted on it. So it is true that particles at rest will not experience any magnetic force. Okay? So let's draw some examples then, so I can show you sort of the nature of this law here to say, okay, well, if they are moving, what type of force do we expect then? Okay, so let's get some magnetic field lines drawn up here. Just use a bit of brown here for the magnetic field lines. Okay, so here we go. Here's some magnetic field lines. And what we'll do now is let's just sort of simply put a charge in it and let's get it moving. Charge in it like this, and let's just get it moving this way. Okay, so here we go. So we've given the charge some speed V now, and of course these brown lines, as I mentioned before, are the magnetic field lines. Okay, so we got it. So as we diagnose the law, let's keep two things in mind here. There is that big nasty cross product in there, and also the cross product can of course be written, if you just want to get a handle on things, QVB, cross product always involves the sine of theta, where theta is the angle between V and B. So we have the law there. Just a couple ways of thinking about it. So here's our first example. If you look at this one here, looks like V is pointing in the same direction as B. The angle between them is 0. Sine of theta is 0, the force will be 0. So this particle here, which is moving along the magnetic field lines, won't have any force on it at all. So if it's moving at, say, some fraction of the speed of light, it's going to maintain exactly that fraction of the speed of light. It will not speed up or slow down. There is no force on it. Likewise would hold for a particle that, say, I launched opposite to the magnetic field line, something like that, if V was that way. Why? Because B is to the right, V is to the left. That's an angle of 180 degrees between them, and sine of 180 is also 0. There'll be no force on it. And there's also interpretations using the cross product that parallel and anti-parallel vectors, in the case of the V's and the B's I've drawn here, have a 0 cross product. Okay? Well, let's get some action going here. How about a particle that's like this, where it's launched up like this? Okay? So the angle between V and B is 90 degrees, so the sine of 90 is 1, so that's not going to cause any 0 force. Okay? So what you have to do now is just an interpretation of the cross product, either using the right-hand rule or a little model like the one I've drawn here, and I've used in a few other videos here. So what we'll do to figure out what V cross B is here is we'll put the A vector on this little model here in the direction of the first vector, which is V. I'll put this vector, the second one, in the direction of the magnetic field, which is going to be over like that. Yeah, sometimes I have to spin the thing, but this is still my first vector, this is still the second vector. And look what I get then. I get this third resultant cross product pointing down and into the page. So that means that a particle like this that's in a magnetic field in this way is going to have a force on it that's down into the page like that, just by notion of the cross product. So this particle here won't even stay in the plane of this whiteboard. It's going to start moving down under the whiteboard. And then, of course, if you want to know what would happen at that point, you have to sort of recalculate or relook at what the force is. But the magnetic force is very three-dimensional. Let's look at a couple more examples like that, like this. Okay, here's a case here. These are B field lines. Well, let me not draw so many circles. It's getting kind of messy, isn't it? Let me just draw a bunch of dots like this and say this is the magnetic field. So we're in the poles of magnet or what have you, but the magnetic field is pointing up at us. So these black lines are the B lines like that. Okay. And what we'll do then is we'll just take a particle like this, proton once again, and we'll just launch it into the magnetic field region with the speed v like that. So the question now is, what kind of force is it going to feel? It's going to be zero, or it's going to do something, or what? Well, F is QV cross B. Let's use the model here. I know the sign of zero isn't going to vanish because even though it's three dimensions here, B is straight up at you, V is over. There is an angle of 90 degrees between them, so the sign of 9 is going to be nice and non-zero. It'll be 1. So we've got to figure out what the force is. Use my model here. I'll put A in the direction of the first vector like that. I'll put B, my second vector, in the direction of the magnetic field. So my model looks like this. First vector V, second vector B, and V cross B. It looks like C, the resultant vector, points down like that. So that's right. What will happen is as soon as the particle enters this magnetic field region, there's going to be a big downwards force on it that's going to look like this. That's going to be the force on it like that. Okay? So what will happen next? Well, the particle will move, but if you have a downwards force and a velocity over like that, that means the velocity vector is going to sort of start turning down to the right. So maybe a second later or something like that, the particle is going to be over here, but its velocity is going to be down to the right a bit. So the velocity is like this now. But it's still in that magnetic field region, so let's see if we can figure out what the force is on it. Get out the cross product tool. A, there it is, my first vector A in the direction of V, because it's V cross B. The upper popsicle stick here, the second one here, is in the direction of B, up like that. So look at where the force is now. It's not down like this anymore. That's the way it was over here. But now because V has changed, this resultant vector has changed. It's going to be sort of down and to the left now. So the particle is going to have a force on it, which is over this way now. And as long as the particle is in that magnetic field region like that, this trend or pattern will continue. So the particle next will be here, and maybe the velocity is straight down now. Maybe it's been steered by that field. And we'll just sort of do this one more time. V cross B, down like this, B is up. Looks like the force now is straight over to the left, straight over that way, to the left like that, just owing to the nature of the cross product like that. So I can draw a big force on it, which is over to the left like this. Look what the shape this particle is going to go in. It's going to go sort of in a trajectory that looks like this. And as long as it stays in that magnetic field, it's just going to make a big circle like that. So that's something that's very sort of first level understanding about the force. The magnetic force on a charged particle tends to steer them in circles like that because of the way this looks here. The reason why you get these circles really has to do with the nature of the cross product itself. So here it is. It's this thing here. No matter what orientation of V and B you have, what orientation, the resultant is always going to be perpendicular to V. Because no matter what I do with A and B, even if these things were squeezed in here, the resultant, which is this one right here, is always going to form a 90-degree angle. Here's that 90-degree angle right in here relative to that velocity vector. In other words, this force law always produces a force here which is perpendicular to V. And if you remember from your mechanics class, this is what produces circular motion. So if you have a charged particle that has a charge and it enters the magnetic field region, they're always going to start going in these circles. There's a lot of kind of interesting examples of that. So like, for instance, we mentioned in another video about the Earth's magnetic field. So the Earth sits here like this, and here's the geographic North Pole and the geographic South Pole right there. But what we know about the geographic North Pole is actually a magnetic South Pole. So in the interior of the Earth, all told, the Earth sort of behaves like this. So here's these magnetic field lines coming out of the Earth like that. So that's sort of what our Earth looks like. So we have these B field lines now. And so what happens then is if a charged particle comes in from outer space, there's often collisions in the upper atmosphere between particles from space and the upper atmosphere, or just some ions happening whizzing by, if they get caught in this magnetic field, say maybe right here, you know what they're going to do is they're going to start circulating around that magnetic field. I didn't draw it very well, and maybe that will or won't be the pattern, but this is the nature of the beast here, because the magnetic force is always perpendicular to the velocity. So if the particle is sort of, I don't know what direction it's going in, but there will always be a perpendicular force, and it's going to start getting into these spirals like that. And whenever something has a force on it like that, that means it has an acceleration on it, and charged particles that are accelerating emit radiation. That's how antennas and so on work. And so what we get out of something like that, because it's spinning around in those circles and always accelerating like that, that's where all these pretty colors come from. I think most of the ones I've ever seen have a lot of green in them, but these colors come out because the particle has an acceleration on it like that. Again, charged particles and magnetic fields, circles, because the force is always perpendicular to V. And there's one last sort of interesting one that you might think about, and it's sort of one that looks like this. Suppose there's a magnetic field like this, and what we do is we're going to take that charged particles. This is our B field like this. That's our B field. What we're going to do, we're going to take the charged particle and we're going to launch it into the B field like this. So here's my proton here going into the B field. So what force do I get? Well, once again, if I use my little model here, it looks like I've got, there's a B vector like that, going straight that way. The magnetic field's up. So I'm going to get a force up like this. So the particles are going to start coming up at me like that. But what that really means is it's going to start going in a circle, because it'll sort of start doing this kind of thing as it goes around like that. So it'll start coming in a circle, and what it'll do, it'll go in a circle like this, it'll sort of come in like this, and it'll sort of come out of the page and turn back around again. So make a big circle and come back out again. So one of the things I just wanted to tell you then is, suppose you launched it in a magnetic field like this. So you didn't make it exactly perpendicular to B. So what will happen is when it comes in like this, now the black arrow here has two components. It has a Vx this way and a Vy like that. So the Vx here will be responsible for that same turnaround that we just sort of visualized in the last example, same turnaround like that. But while it turns around like this, the Vy here is going to cause it to sort of start drifting up like that. So it's going to turn around like this, but it'll make a corkscrew motion like that. Sort of start going up like that. So remember, this motion here is because of the y component of velocity right here, but the circle here, that's due to the Vx motion, the x component of velocity. So it'll drift up like that, have some circular motion, so you get these corkscrews for particles entering magnetic fields. And these are the types of trajectories that those charged particles from outer space sort of execute as they enter the Earth's magnetic field. And all of these sort of turns and kinks, the reason why it stays in circle is because it's accelerating. And so that's sort of another sort of idea out there, that whenever charges accelerate, radiation comes off of them. They generate radiation. Comes out, something like that, become little radio transmitters. And in the case of the northern lights, you can actually see it with your eyes. So anyway, that's the magnetic force law, QV cross B.